what we were discussing previously was the correspondence between an entailment, between a proof fished from the entailment cone and one found by automated theorem proving, right?
Yeah.
Okay, so one of the questions is, can we find ones that have the same structure, or will they, like this parallel structure here, is a little different? Will we find ones that have the same structure, or is it inevitable that we have a different structure here? See
We
what
can
I'm saying?
totally find the same structure.
I'm sorry, say that again?
You can totally find the same structure.
All right, well, let's find an example which has the same structure then. So where had we done this? We had done this in, okay, this was a completely different thing. Okay, let's get out of that one for now.
I have a few in the new notebook.
Oh, which new notebook?
It's like the one with James, Nick plus James draft issues.
Okay.
I had the like Boolean axioms.
Okay, wait. Where is this now?
Yeah, that one, issues 2,
Yeah.
right? Right.
Yeah.
Yeah.
I think it's number 18 somewhere. 18, yes.
This isn't ready, by the way. You're just kind of taking a peek into something that's just begun.
Yeah, by the way, when you have something that's this slow to scroll, you can put the kind of really huge assets in a different notebook, and you can put a summary in here as bitmaps, right?
Good idea. Yeah, right. Nick, didn't you say it was 18?
Yeah, 18.
I went past because I was so excited. Okay. Well, Boolean axioms is very big, so let's hope that we can get one that's a little bit less, just a single axiom, for example. Oh, you've got one there. Proofs, no, that's proofs from the Boolean axioms of that result.
Yes.
Right? Okay, but what we're looking for here is one like this, where we've got just maybe we need one where there's an equal amount of stuff on both sides. I don't know what the right thing is. You know what I'm saying? Have we already looked at this? We looked at this in 60, I believe. Was it in 60 or was it somewhere else? Was it in 66? This is not it. Okay, let's look at where do you think it was?
I'm not sure. I can start looking too.
I, by the way, did adjust the section on
Motion?
No. I adjusted the section for that thing you found, although I couldn't re-find it. Well, no, maybe I did re-find it. The one where you found the idempotence things.
Oh, good. Okay, cool.
the distance matrix between proof steps. I like the term hand-woven fabric. Let me just make a note of that. It's in a different section.
Nick, do you remember us doing this before? No. Do you have any instincts regarding how we might begin?
Well, I mean, those are the things for which we were running the Amazon jobs.
I was running a bunch of Amazon jobs today too, unrelated though.
Did they work?
Oh, I finally made them work.
Okay, there's some notes here which are, I think I was really tired when I was writing that empirical mathematics section. I think we need to retry there. Oh, there are Amazon jobs. Okay, there's an example of a super simple proof. Of a fairly complicated thing from that axiom. Okay, so let's go up here. So this is a case where we are allowing both substitution. We should allow both substitution and by substitution.
Okay.
I didn't allow. That by substitution is already a contained substitution.
I know, but
No, that's not the, I think what Steven means is let's not just use substitution,
well,
right?
okay, so let's do the following. Let's get, okay, I think we're going to have to do a search here. Let's see a choice here. So are we going to try and use this axiom, or do you think it's better to use an axiom where we don't generate variables? What do you think? I think it might be better to not generate variables. Do you agree?
Yeah. If you can find it there, then it's going to be clearer. What kind of search do you want?
Well, wait a minute. I don't know exactly yet. Hold on 1 second. Let's try. Are we going to try that axiom or something different? Okay, so we've already discussed proofs and accumulative systems here, but we haven't discussed Right. So this is proofs in accumulative systems. And wait a minute. Oh, we started off discussing this axiom, and then we kind of but we found that in the entailment cone. So why the hell did we go back to talking about a different? Okay, so wait a minute. So let's look at the proof here. Of this result given A dot B
B. Right. Ah. Okay.
Well, what else could we try to prove in the entailment cone here? So this entailment cone, oh, wait a minute. This is, I'm totally confused. Okay, what we need to compare this to, right, is this instead. We need to compare it. This was a path, right?
Yes.
Now we want to do the token event graph from this. See what I'm saying?
Okay. Mm.
And the question is, do you see what I'm saying? Whether we get to, given this, okay. Now, let's look at this relation here. Do you have a function that turns this into rules?
Yeah. But the one that paternifies it. You have to include what symbols? Yeah.
No, but it's still not a two-way rule, right?
Okay, then here we put that into this. Okay, so where is that thing? Do you get what I'm asking?
Yes. Yes, I understand.
Well, I have no idea whether this is the canonical form. This might not be. Oh, don't I have to say canonicalize?
Oh yeah, try it. And maybe a sort. Canonicalized patterns. It's the same one.
Well, do we need to say sorted?
Yeah. Maybe it has a sorted version.
You know what? I think we need to do this. Oh, come on.
Where's so sure it should be there?
I'm not sure it should be there. I was just hoping it would be there. Okay, let's pick something that is there, okay?
That's a good
So-
idea. Yeah, right.
I have no idea whether this one occurs early or not, but let's take a look at that one there.
Wait, that's the actual,
Oh, that's incredibly boring. That's the actual axiom.
yeah.
Well, let's take something like this.
Sure.
Okay, so how do we get that into a form that, what is that? Symbolify patterns?
Right.
What?
Need another parenthesis.
Yeah, but why is that? What the hell? What's going on?
Maybe there's no. Oh, it can find it.
But we know it's entailed.
Have you copied it correctly? Where is it?
Well, I'm not sure. Let's see. AB.A.
Oh, there it is. Oh
No,
no,
where?
you're missing one A there. If it's the same one, like fourth line from the bottom. It's almost the same. Yeah, this one.
Oh,
It has A.
yeah. Well, that's not terrible. That's not terrible. Now let's do the extracted proof from here.
Wait, you have a different axiom.
Oh, fuffle. That's not horrible. So let's I mean, it's a slightly different structure, but it's not totally different. Let's canonicalize this axiom. How do we do that? We just say canonicalize symbols. Is that right? No.
Patterns.
Great.
Okay, what do you think of those two? Okay, let's go with these two. So then what
Right.
we're explaining is that this is a slightly different structure. Let's look at. Okay, so we know that all the ones in here are basically going to look like this, more or less. Let's just do this. Let's just do this across all of them, okay? Let's just do this across all things
Yeah.
that are this thing here. Okay, so here we've got this. Let's just say, okay, so here I want to say symbolify patterns. Yes, is that right? Is that what it's called? Is that right, Nick? Does it need variables?
Doesn't it?
No.
It doesn't. Oh, okay.
You turn patterns into symbols, just don't
Okay,
need
all
them.
right, okay. All right, so that's the second piece. And the first piece is this find a cumulative proof, right?
Right.
Is there some pre-computation that we could do for this, or should we not bother?
It's better to pre-compute the graph and then just use find proof directly.
Okay. Okay, so the entailment graph is this thing here, correct?
Yes, cumulative token and graph.
Okay, so we do just substitution for now.
Okay.
Let's do that.
Okay. Mhm.
Now we want to say vertex list of EG two-way rule. Okay, those are our
Okay.
targets. Okay, so now here, what should I do? I should say just find proof.
Yeah, find proof that graph axioms appear.
Find proof doesn't seem to exist. Is it
Lowercase
lowercase?
f. Yeah.
The graph. And then what do I have to give? Do I give the axioms or not?
Yeah, and the conjecture.
Right, the graph, then the axioms.
Yes.
right?
Yes. Yeah. Graph, axioms, hypothesis.
And do I need to give the S and so on there?
No, no, no. You already computed the graph. Just searches for the subgraph.
Okay, do I need the two-way rule fix or not?
Oh, if you want. If you, how do you use it?
I'm not sure. So this is now, that's not promising. Something has gone wrong here. Okay. All right, let's take one of these. Okay, so let's say find proof in EG. Do I really need the axioms there? Why do I need the axioms?
Or how would it know when to stop? No, because it backtracks from your hypothesis until it finds the axioms.
Oh, okay. Should I give the hypothesis in,
No, no, it's just one hypothesis.
no, there it is. I've got one hypothesis there.
Yep. I think it find occasional proof that.
Okay, so let's look at symbolified patterns.
Maybe you need for all.
I don't think I do. But well, maybe I do. Symbolified patterns. Oh, big puffaleffel.
Quality. Just true.
What gave just true?
No, some of them, some of the vertices.
Of what?
So I call the first one. The first one.
Oh, there could be some that are identical here. Okay, so here we want to say delete cases of this x blank, two-way rule x blank. Okay, what's that first thing? Oh, first of two-way rule. So how do I make the graph here?
Just graph or subgraph of original graph. Well, subgraph not gonna work, just try graph.
I don't think that will work because that's not going to give the right look, is it?
Not the right look, but yeah, we have to like.
Or why don't we
it
just do
sense.
subgraph of no, wait a minute. Graph. Look, let's do subgraph of EG. Oh, for God's freaking sake.
Because your two-way rule fixed it.
What does that mean?
Now the vertices are different now. Don't fix them.
Do I need the first or not?
Yes, because it's a list of proofs. Okay.
Okay.
Oh, you can token labeling true for original graph. That shouldn't hurt much. If it's not, yeah.
Okay, so here I want to say parallel map. Oh, for God's sake. This here, we need to say distributed contexts, arrow. Is that right?
Backtick. Wolfram backtick.
No, isn't it this?
No, you need another one. Like
Here?
it was, yeah, between them. Yeah.
Really?
Yeah.
Okay. Let's go all the way here.
Okay.
All right, so what we're going to do here is we're going to show some where the structure is kind of similar. And then somewhere it's different. Okay, so let's say we have two. What was the one we were looking at, which had 2 and 2? Well, that one has 2 and 2. Has an awfully long conclusion. What was the one we were already looking at that had 2 and 2?
You have it somewhere on the top, right?
This one here, yes. Okay, all right, well, let's use this one then. Okay, except that thing, where does this appear in the entailment graph? Does it appear in an interesting place? No, it appeared at that level. I want one that appears at the second level. You see what I'm saying?
Wait, that dot's just for the boring one.
Oh,
That's for the
oh.
axiom itself.
Ta-da, nice, okay. So we probably need to clean up that. Okay, here goes then. So we want to start with this axiom. Starting with the axiom, okay, so now we want the token event graph here. And the axiom we want to start with is this one here. After 2 steps, okay, we need to, I don't think we need to highlight the subgraph actually. But we do need to clean up the,
Yes, the layering.
well, okay, maybe we do want the subgraph. How would we indicate the subgraph here?
Can we highlight it?
Well, I guess we highlight it using the same, because it is in fact this subgraph here. Does that make sense?
Sure.
Okay, let's try.
Now, do we want the two-way rule fixed and all that kind of stuff? Or do we need to leave that out?
Maybe
Yeah.
for both graphs.
What, leave it out for both or
No,
put it in for
apply
both? Yeah,
apply
okay.
two-way fix for both. Two-way rule.
Oh, beautiful.
Good. Yeah, I mean, it needs to be a little thicker, I think.
Yeah,
but,
yeah. That's the reality.
Look, when we're near the end of this, it's like, if you don't make the comment now, when will it be made?
Oh, I know. I know. That's fairly reasonable.
While we're at it, do you think that highlighted vertex is too big?
Not really. I think it's important that it's a highlighted vertex. Okay, so that's this, right?
Should be.
With event deduplication to true.
Why is it so wide when that happens?
Okay.
Okay.
Subtracting the subgraph we get, which we can view as a proof of the statement within this axiom system. But now, let's use automated theorem proving. Form find equational proof to get a proof of the same statement, of this same statement. Look, you see this? It has more space around those things. That's something that has to be fixed. See that? That's a general thing. In these token event graphs, there's more space than around the thing in this case. See what I'm saying?
Yes. Yes.
Well, I apply it explicitly somewhere. I have a function that reduces the size.
Okay. Okay. Here's what we get. This is again a token event graph. But its structure is slightly different from the one we, quote, fished out of the entailment cone. Essentially what we see is that instead of starting from the axiom and progressively deriving our statement, we start from both the axiom and both the statement and the axiom, and then show that together they lead, quotes, via substitution, merely via substitution, to an expression, to a statement of the form x equals x, which we can take as an, quotes, obviously valid tautology.
Good.
Okay, now let's show a couple more slightly more elaborate examples.
Okay. Now you had that note about Nick was explaining that this is done basically because it's efficient for search, And
Yeah,
you made a comment about the objective function.
yeah, we'll deal with that just a
Okay.
second. Okay, what about this guy here? This guy looks very ornate.
Okay.
Sometimes the minimal direct proof found from the entailment cone can be considerably simpler than the one found by one-minute theorem proving, say, with find equational proof. Oops, I don't want that one. It's too much. I want one like this, I think. Okay. How do I get to this one? Oh, for goodness sake. Eek.
Just
One,
its
two,
positions.
three.
Okay, you count them.
Okay, let's do it a different way.
Double comma.
Huffle.
What the? What?
Did I get 203 right?
Yes. Why?
Which one were we looking at? We were looking at that one there, right?
Yes. Nick, any instincts?
Not yet.
It's probably because of the blanks. Maybe if I say verbatim of that.
Isn't graph atomic?
I'm sorry?
Isn't graph atomic? Graphs.
Yeah, it should be. Okay, anyway. Let's just not use technology. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12,
And
minus
negative
12.
My God, we're counting.
Shh. Shush. It's been done by humans for millions of years. Not
You know,
millions of years.
one time.
No, minus 12. Excuse me a second. Go ahead. Yeah. What are you saying?
No, I was just going to say, one time I counted something by hand and then I caught myself and I thought, if Stephen ever found out about this.
Yeah,
Stephen never
usually one
knew.
gets it wrong. Well, usually one gets it wrong. I got to say, usually one gets it wrong if one does it by hand. Okay. How do we get this? Is it symbolify patterns of that? Oops. For example, the statement appears for example, for the statement, the direct proof what's happening? Oh, for goodness sake.
What?
I left the comma out. Why is that different?
Is it the right rule?
Yeah.
It is. Okay.
You know, the sizes of these dots really need to be adjusted.
Nick, how can we do that?
Sometimes the middle direct proof can be considerably simpler. It can be simpler. For example, for the statement, the direct proof is while the one found by find equational proof is Okay, now what we've got to say is, now we're going to have an example where you just, it's far down in the entailment cone. There is a proof, but it's a long, long, long proof.
Yeah.
Right? So we want a theorem for this,
Mhm.
which exists, but it's a long theorem. So we really want to go searching for the theorems of this axiom system.
Okay.
Okay, so we've done a lot of axiom searches before. And where do we have those? We have those. Do you agree that this is a reasonable thing to do? So what we want to do then is to find okay, so we're search for a theorem that cannot be found from the entailment cone. Didn't we have some examples? We had the examples later on where the one made theorem proving where we have with the natural life axiom systems, but we want an example here.
Oh, wait, you mean it can't easily be found?
Yeah.
Like it's there, but we're not
Yeah,
going
yeah,
to find
it's
it. Yeah, yeah, okay,
right.
just making sure.
But the great advantage of automated theorem proving is that it can find proofs that it can do directedly search for proofs
Yeah.
rather than having to, quotes, fish them out of a potentially huge entailment cone.
Yeah, and the entailment cone is basically an exhaustive method.
Right.
And this is, I
Rather than
remember.
having to fix, okay,
Yeah.
out of the, fish them out of what is in effect directly, but the great advantage of automated theorem proving is that it can directly search for proofs rather than having to fish proofs
Exhaustively.
out of the entailment cone, out of the exhaustively generated collection in the entailment cone.
Yeah.
Rather than having to fish them
Mm.
out of the entailment cone, directly search for proofs, rather than so it can directly search for proofs instead of just
Mhm.
fishing them out of the entailment cone in which all possible proofs have been exhaustively generated.
Yeah.
So instead of just fishing them out of the entailment cone that contains all possible exhaustively in a sense, to use automated theorem proving, you have to quotes know where you want to go, and in effect have a hypothesis about a theorem. In a sense, have a hypothesis about what might be a theorem. What might be a theorem?
I remember I saw a talk by Papa Demetrio on P versus NP once, and he was comparing with exhaustive search, this thing called telescoping search. That's how he was describing P. I kind of like that term. With this, it's kind of like basically have your proof telescope, and you just kind of like, if you know where you want to point it, you can kind of point it, and then
Yes.
you have this lens that allows you to see farther. But if you don't know where to point it, you have to kind of just exhaustively
Right.
search
Yeah.
for everything.
Right. To use automated theorem proving, you have to, quotes, know where you want to go, or in effect, identify the theorem you want to prove. To use automated theorem, perfect. Okay. The hell is this? I see, that's a complicated tautology. Okay, so let's now go to the next thing we want here. Okay, the next thing we want is a complicated to find exhaustively theorem. Okay, then we might want theorem one can guess from known mathematics, possibly.
What do you mean exactly?
Well, I mean, like what are you trying to prove about NAND? Well, you're trying to prove, you know what I'm saying? Without knowing the mathematics, without knowing the existing mathematics, you have no idea what theorem to go and try and prove.
Oh, I see.
Let's go back here. I don't think we're going to bother with that. Then, okay, we want by substitution.
Okay.
We're going to talk about completion.
Mm-hmm.
And we're probably going to talk about cut elimination.
Mm-hmm.
Okay.
Now for this complicated theorem that we're going to find exhaustively, do you want to represent it graphically, or do you just want to find it?
No. I want to represent it using a picture like this.
Okay.
Okay.
Oh,
Okay. So the thing I want to do is we're going to search among. So, I mean, we've done this like a million times, searching through possible theorems. I'm trying to remember where we've done one of these searches. We've got, I don't know why there are those things there. Oh, those are other axioms. Yeah. We did. Okay. So let's get, okay. So let's say we've got tuples. Should we do AB or should we do ABC for the theorem? Nick, do you have any opinion about that?
No. But you've done it so many times. This is a function that just generates theorems.
Yeah.
It's called all theorems. You should try it.
Is it called all theorems?
yeah.
So it's like a number of variables, just a list of variables. And a number.
How convenient. Okay. So, and I've clearly done it with find equational proof a million times as well.
Yeah.
Do we have the code for that someplace? Okay, so what we want is a long proof graph. We've done this like a million times.
Yeah, I see them in 66.
Oh, look at that. We've done it for this. Is this the right thing? No, X, Y. Look at that. Is that the right axiom system or not? The hell is that one?
Is that your axiom?
A dot B. And we could use that instead of the thing we've been using.
Uh, won't that be variable generating?
Oh, we want to generate statements. We don't actually want to generate axioms. We want to generate statements.
Then it's just all expressions.
Okay. Well, it's basically this. Come on. What is it doing? How can it take a long time? There's a time constraint error of 4 there.
Now, how many statements is that?
Well, it's 465, it says there. Let's hope there are no stupid stragglers.
Yeah. Okay. Underwhelming.
What's that?
Not that interesting looking, are they?
No. Right, let's look over here at what we found before. That was a more complicated axiom system. But some of these are interesting. That was critical pair lemmas, but let's look up here. That's A equals A dot B. Okay, so let's think about this. So what we're trying to do, let's just try the case where we have a C,
Okay.
generate statements A, B, C, and let's just say 2, and let's see how many there are there.
Can you try all expressions instead of generate statements and just see the difference? Because there are two definitions. I don't know what's the difference.
Expressions is just that.
All theorems then.
Well, I think all theorems may be better. I think it may have pruned a bunch of stuff down.
Yeah, it's like up to canonical.
Yeah.
Okay.
It's thoroughly boring. So this is take largest by proof length, right?
Yeah.
Well, let's just try this again. Maybe we can try 5. Let's see how long that is.
Oh, no.
That's not a good sign.
No.
Well, maybe we can just check that this actually gave what we thought it gave. Can we finish? Oh, for goodness sake. Those are super trivial.
What do you think? Should we do a different axiom?
I think we might. So this one here, A equals A dot B.
Okay.
For which we now have non-trivial things. Okay. So we're confident of having some somewhat non-trivial stuff there. well, actually, we don't know that these aren't just inefficient ways to get. All right, A equals A dot B. I mean, is that non-trivial? We don't know. Um, um, well, none of these are non-trivial. Well, that's another one of these A dot B things. Okay, let's clean out the stuff we know isn't interesting.
Good. Okay. Outtakes?
Let's find outtakes. Tis the way.
Are there NKS outtakes, by the way?
I don't know. There's some NKS chapters, like there's a chapter 13 that never got finished. Might try to do.
What was the topic?
What will happen next?
Ah, well, it's easier to write that now.
What's that?
It's easier to write that now.
It is easier to write it now. Much easier to write it now. No, I predicted 20 years before the next major sort of stage would happen. And here we are. Of course, I didn't predict that I'd have to be the one doing it.
Well,
actually, I'm perfectly happy. I mean, it's a perfectly good conclusion.
Well, I was about to say, I mean, would you rather
I'm
that
fine.
it was, you know,
person,
you know,
X.
Doyne Farmer or someone who's doing it?
Yeah, right. Well, I think it's more likely to be the young, your generation. Okay.
Well, I mean, we are involved.
Indeed, which is very good, which is why it's all happening. Otherwise I'd just be a okay. Anyway, so let's
Yes. Okay.
So the only question is whether these are actually non-trivial. Because we don't even know whether some of these things occur in the entailment cone. Right, let's find out if this occurs in the entailment cone. I mean, we could also just find out whether anything that's a small number of steps has got to occur in the entailment cone.
But yeah, but can we actually generate that cone? I mean,
Sure,
how
we
many
can
steps?
generate that cone.
Okay. But how many steps in it is that? For that particular one that we're about to consider?
Who knows? I mean, who knows? We don't know because this might be an inefficient proof.
Let's hope.
Well, let's not hope. Let's hope that this isn't accessible because that's kind of what we want, is one that isn't accessible.
Oh, I thought you wanted to find one that's accessible, but it's noticeably deep. But I guess that's something that's kind of difficult to show, right?
No, I mean, we want to find one where it so happens to use automated theorem proving, you have to know where you want to go and in particular identify the theorem you want to prove. Okay, so how the hell are we going to do that? I mean, in other words,
What do you mean?
well, because we don't, other than by using mathematics, how do we know what we're trying to prove other than by an exhaustive search? Oh, I know how we can do it. We can use models.
Go on.
Okay, hold on. Let me think how to do this. We can do this with models.
Sounds cool. Okay.
That's exactly what I did for the Boolean algebra thing.
Now wait. This section on model theory.
Okay, look at this. You see, we're predicting which theorems will be true based on models.
Yeah. And we have those dots, by the way.
Okay, well, fine. Just hold on a second. This is model theorem. Okay, we need the function model theorem. Okay, so here we've got this.
But wait. This
Where is
section,
model? Yeah.
have models been introduced yet in the
No,
blog?
I'm not going to admit that we're using models. I'm just going to use models privately.
What, behind the scenes? Okay.
Yeah, to say, here's this theorem. Where did it come from? Who knows? Right? That's sort of the whole point. Okay, so where is model theorem?
I think we have it in our notebook because they have it.
Oh, yeah. Okay, that's probably an all theorems play.
Yes.
Probably a cleaner version of it. Okay, so now we want to say what is this doing? Let's just have a simpler version of this. Okay, hold on. We want to know for a particular axiom system here. So in particular, this axiom system.
You want to do it for that one?
I want to do it for that one because that's the one we've already got examples for. So if we can do it for this one, we're in much better shape.
Indeed.
So for that axiom system, I don't quite understand that and where the parallel map is coming in there. Oh, that's all st, comma 4. Let's see, comma 30. Okay. Why are they all false? Let's take a theorem we know is true. Like this one here.
Good.
Okay, so the basic problem is that there aren't a lot of true theorems in this business, but let's take a look in the model theorem here. Let's define a new parallel model theorem. In which that mapping over theorems is parallel.
Mm-hmm.
Okay, now we want to say all theorems, AB, comma 4, for example, and that's 3050 theorems. Okay, so let's say parallel model theorem of axiom here.
Maybe cache models of an axiom.
Say that again?
Maybe cache it, all the models for the axiom, right? Because you only have one axiom. So you just need one code to find finite models.
I've got it here.
Yeah, but you, okay, it's one time, right?
Yeah.
Okay, yeah. Sorry.
Okay, now let's say okay, there are theorems. So now we need to do this puppy. Not over all theorems, but over %247. Stunningly boring. Although we do at least have some bisubstitutions happening here.
Yeah, but they're of the most trivial sort.
I know. All right.
But it's progress, I suppose.
But let's keep going here.
Yeah.
So parallel model theorem. This here. So we really want all theorems ABC, comma 2, for example. Okay, so let's go all theorems ABC, comma 3. The hell is that? Why do you think we have that?
Sure.
Okay, so here, oh, look at that, silly me. I am not optimistic about those, especially since they only contain two variables. Well,
Or you can get more because your axiom is not variable generating.
Why don't we
why don't we try
consider
the
the
other
case
axiom?
of a variable generating axiom?
What was the other one that we were looking at over here?
A two-way rule.
A
dot-
equals
yeah,
A dot
yeah.
this one here.
Yes. Let's do that.
Okay, so parallel model theorem. This thing here, all theorems AB4. I'll just do AB3 here, first of all. Okay, now here, right, that's that. Well, there's a slightly more complicated one there. It's not thrillingly exciting, but it's a little bit more complicated.
Isn't the desideratum basically you want by substitution, but not in the first iteration? That's
Well,
basically what we want.
I actually prefer to have no by substitution at all, but let's just try.
What?
Okay,
But
I mean,
just the other test, you said, "Hey, look, we found one."
I know.
Okay,
But that was a
times have
different
changed.
thing.
Yeah, okay.
It was a different thing. That was a different thing. Oh, these are looking a little bit jollier.
Yes. Do you want to compare against cones yet, or do you want to keep going?
I want to know what would happen if we used my Boolean algebra axiom for this.
Okay.
Okay. Or something of similar complexity. See what I'm saying?
Yeah.
Because I know that that one gives non-trivial how do I do unformalize? I want to do this slash dot center dot goes to small circle. And then anything else I want to change there. Well, let's do the unformalized symbols. Is it unformalized symbols?
Yeah, I believe so.
Why that doesn't autocomplete, I have no idea. Okay. My God. Let's just go ahead and say extract 84 comma this. Actually, we don't even need to do this. We don't even need to do theorem proving. Well, we could do models, but we could just enumerate, because we know this is Boolean algebra. We could just use Boolean algebra to evaluate these. Okay, now just for the hell of it, let's do this. Oh God, there's 3,000 of these things. Well, what the hell? They're probably mostly pretty simple.
By the way, here's a question. If you generate all the models for the Wolfram axiom and the Boolean axioms, are they always the same?
Yes,
How do you know that?
because it's proved. Because that's what it means to prove that these axioms are equivalent to Boolean algebra.
I think it's, well, maybe you proved that it contains it. Maybe there's some model that your axiom satisfies, but not the Wolfram Boolean axioms. Can this be the case?
No, it's proved both ways around.
Oh, both ways. Okay.
In other words, the Scheffer axioms satisfy this, and this satisfies the Scheffer axioms. So insofar as those axioms, yeah, I think it's proved both ways around. Has to be. Cannot contain. I wonder whether any of these are going to be significantly complicated. They might be. And they might be complicated enough we don't manage to make it in the 4-second timeout. It's another possibility.
Okay.
Da-da, da-da-da. Wowee. Now, why didn't this generate? Take largest by proof length. Oh God, what happened is we didn't manage to get very many of these things proved.
Yeah, time constraints. Sure.
Didn't we do this already in ATP 66?
No, we did a different thing. We took things which were already showed up in the axioms of, yeah, so this is a lovely result. This is lovely. I mean, this is, but let's try to do this. So this suggests that with slightly more complicated axiom systems, we should be able to get significantly better things happening. Okay, so what do we think we want to do? Let's try b.c.a or something equals a. I don't know. Okay, so let's try b.c.b equals a, just for fun. That was very fast.
We just
Oh, probably because there weren't very many models. That would be my guess. And let's think what we want to do to get. So this is a 3-variable creature. I mean, I'll admit here that we're guessing axioms using guessing results using if this works. I need a piece of food while the computer is eating too. I'll be right back.
Nick, did you get any more sleep?
no. No, I haven't slept.
No nap? No. This is what happens when you have to suddenly change your sleep schedule. This is what happened to me the first day of the winter school on January 3rd. It was like the night of January 2nd. I went to bed at like 4 o'clock in the morning, right? But then in order to wake up at 6 in the morning, right, for the winter school, it was like I had to wake up only 2 hours later than when I usually went to bed. I was going to bed at 4, and then I had to start waking up at 6. So that was a radical change. And I was pretty exhausted that first day.
I can imagine. Yeah.
You know, no, never mind. So what's happening with this quantum framework group? Are you trying to finish something this week? Are you starting something new?
Hi there.
Hi.
I see. All right, we have some results. Oh, okay.
We got juice here.
Yes, that's quite nice.
That's very juicy. Even almost too juicy.
No, I think it's okay.
That's very long.
Well,
All right.
if you
all right.
remove the token labeling, it might be okay.
I know, but
I mean, it's still long, but it'll be less wide. And
gosh. Well, so
this, yeah.
what's happening here? All right. So let's try one more iteration of trying to make something simpler. Let's try removing try removing that dot B there.
You want to make them like shorter? Simpler?
No, I want to make this axiom simpler. Oh God, we made a horrible mistake here. We
What?
didn't change the thing we're proving with here. See what I'm saying?
Yeah, I see.
These are proved with our axioms so we proved it with the axioms of Boolean algebra, which doesn't really.
Less juice.
Uninspiring.
Dang it.
Wow. So Boolean algebra is looking to have very high proof complexity.
Yeah, right.
Maybe we found something special about Boolean algebra. That would be very exciting. I mean, we haven't known anything special about Boolean algebra.
Interesting. We might want to compare it with another well-known axiom system.
No. You can just take that. Okay, yeah. Just do this. Let me not make that mistake again. All right, let us just make AXX equals, let's just monkey with one thing. Okay, let's just make that an A. Okay.
Okay. Come on. Oh, painful.
That's odd. Well, they're either too complicated.
Mhm.
What do we think here? Should we try one with a longer timeout? Let's try just one with a longer timeout. I think we could try doing is to see whether if we increase the size of the models here, Sorry, just dealing with it. I give up. I mean,
I wish we could get a progress bar for non-parallel computations.
we're trying.
Oh, you are? Okay, cool.
I don't know how realistic this is. This is size 4 models. See if we can reduce the number from 543 to something smaller. All right, so this was an attempt to monkey with the Boolean axioms to get, so this is a pipeline that we have here. God, why is the size 4 models being? Oh, for goodness sake. Really? Yeah, let's do percent. Wow. Okay, then these are probably true. Wow, that's crazy. But none of them can be proved with the automated theorem prover?
In 4 seconds
No. I mean,
or
and
higher. Yeah.
what we were doing now. I mean, so
Yeah.
let's just try. Let's take a random sample. Let's do 150 of them because that's how many we can do. And then let's say, we do AXX is the right thing here. Yes, it's the same thing. All right, let's give it how much? Let's give it 30 seconds or something. I actually have to think about something else for a minute here. So give me okay, let's have this launch. I'm going to just think about something else for a minute, okay?
Okay.
Okay. Wow. Wow, Splatterorius. Well, so much for that. Okay, so this can't be found. So then what the heck's going on here? Do we think these are, you know, these are like true but have unbelievably complicated proofs? Well, so that does suggest that the Boolean algebra axioms aren't okay, so we want to try an axiom. So this one wasn't good enough, right?
That's right.
So let's just try adding a little bit of hair to that puppy, so to speak.
What kind of hair?
I don't know. Maybe it should be a okay, so this one was okay, so let's try something like b dot oops b dot a dot a.
I see, that kind of hair.
Yeah.
Okay.
I don't know. I'm just going to try a dot a there. It's kind of interesting that there's so few. Boring. Well, you know the saying. When in doubt, ruliate. Okay, what are we going to do here? How big is that? So that one wasn't enough. So let's try. So fast. Notice that all of those are the same length, which I find a bit suspicious. Well, I think there's something a little bit wrong with that. So let's try here. I mean, I'm just. See, I think, unfortunately, one of the things that can happen is that we are looking for very symmetrical kinds of things. Well, I mean, okay, there's at least ones of different lengths, I think. Okay. Hard to know why that happens. I mean, let's just try 10-second timeouts.
Yeah. Ah.
Oh, no, that's because percent was wrong.
Oh, yeah, right.
Okay. Let's look at the actual one for Boolean algebra, which we can use if we have to. It is interesting, though, that this one is somewhat more special than I had thought it was. All right, let's see what happens if we just do something like this. Okay. I'm just trying to get a sense of whether it really is precisely that one that does it. I mean, if it is, it really needs to be studied. Possibly not for this post or anything. And what would it mean if that is the unique one? I think this is going to be non-trivial. But how could it not be? What the hell is it doing?
Rendering.
I know.
Oh, sorry. It's rhetorical. Oh. Great.
That's pleasantly complicated. Okay, so this is
We have
slightly
absolutely
different.
no idea why it worked for this one and not for other ones.
We have no idea. We have absolutely flamingly no idea. However, it is cool that we can guess we just guess a theorem here. I wonder whether any of those theorems are nice and short. Let's just see. Oh, look, there's a very short one. That's quite swank.
What the hypothesis?
Yeah.
Yeah, not too bad.
Short enough that we might be able to, okay, so let's just say.
But look at it. Look at it.
What?
A dot A two-way rule B dot B dot B dot B.
What about it?
Wow.
I don't think you should be
No, I'm not scoffing at the theorem, but I'm just wondering what you would do with it. I mean,
well, here's one that's not trivial.
absurd, right?
That one there. Okay, so that one there is A dot A equals B dot.
A dot A dot A. Yeah, okay, that's better.
Okay, let's sort by 91. My God, those are ridiculously long.
That one has an interesting structure. Look at that.
Yeah, it does.
I like that one.
Yeah, I do too. Right.
I like that one too. Hey, these are kind
Okay.
of neat.
The hunters are finding their prey. Okay.
Yeah, the monkey found juice. Yes.
Okay. Let's try one more time. Okay. But this is probably going to be it.
What? You're going to increase the
No, I'm going to change the thing once.
Okay.
But this is almost certainly going to be it. Okay, so we've got C dot A there. So the only thing I can imagine is removing that B there.
Oh. Yeah.
They're respectable. That's perfectly respectable. That's a decent number of
Yeah,
steps.
actually, we haven't seen something like that before. They've either been puny or quite expansive. These are moderate. Yeah, okay.
I think this one is decent. And we can do both of them. And we can just say,
Okay, we have results. This is
okay, so let's do a sort by here. Is that the one we were looking at?
when
Just now.
one that we like.
Yeah,
No, it
close
was
to it
it was
now.
busier than that.
Yeah, but this is not a bad one. This is really not bad.
No, not bad.
And there's no frigging way this is going to show up in the entailment cone. We should probably check, but it won't show up. Okay, just for pure cleanliness of like, why did you possibly pick that axiom system? I'm going to try. Well, actually, one thing we could do is to well, no, let's do this. One last thing he says.
Yes.
And we can get rid of one parenthesis there. Okay, this is a really strange business, you know? Okay, we're going to use this one.
Okay.
Okay. Consider, for example, this. I love the way that one can just do this. We said just say, consider this axiom system. It's like, why?
Well, it's not always like that. Sometimes it's quite clear how you got it.
Sometimes. Let's make that B, C, just for cleanliness. See, that's what is amusing in the NKS book, because there's just a lot of places where that now it doesn't care whether it's a B or a C here, better not. And the sort by.
Yeah, right. That's the thing about NKS. You wonder, did that take 10 minutes to find or 2 years?
Yeah.
You don't know. I mean, you know, but the reader doesn't know. And it's actually hard to tell sometimes.
Yes, I know. I know. It's a point I should make in the let's consider the axiom here's a theorem that was found by techniques we're not going to explain. No, wait a second. How am I going to say this? You have to know where you want to go. Here's consider the axiom and the theorem. This theorem doesn't show up. Well, we're going to check this. Even looking at, even growing, the theorem doesn't show up in the first few steps of the entailment cone for the axiom, even though I'm making this up. Millions of other theorems do.
Wait, no, why say that?
Because we're going to check it. We're going to check this. Right?
Okay.
Never say something like that without checking it.
Yeah, okay.
This theorem doesn't show up in the first few steps of the entailment cone. Even though millions of other theorems do. But automated theorem proving finds a proof, albeit a slightly complicated one. Okay, so here we want to say what is it? Proof graph, proof object to token event graph. And now here we want to say graph with that vertex thing. Vertex labels, arrow, and now here, an attempt to have those labels not crash into each other. We want to say my God.
Okay. That's just a general measure that has to be applied.
Yeah.
That making the axioms light green and
Wait. How does this prove it? What's that result at the end?
That's not a tautology. Where's the tautology?
I don't
What
know.
happened here?
So how is the original proof graph looks?
Let's just see all of this.
Yes. Yes.
You know what? The A equals B substitution lemma is sort of garbage.
It's a virus.
And I'm just incorrectly recovering the conclusion from through, because I'm trying to reconstruct it using those lemmas.
Okay, so is this in fact an incorrect proof? This probably is an incorrect proof, isn't it?
No, it's a correct proof. It's just you can you can get a tautology easily. I just not doing it correctly there.
Okay, fine. So this is just a fix that we need to make to get the tautology right here. Do
Yeah,
you think so?
yeah, I think so.
So A equals B. But if A equals B here, it's not self-evident you can get a tautology from that. Well, let's just see
You
if
know,
there's
there are plenty of examples where we get tautologies.
yeah,
here.
so let's just find another example.
Even the next door neighbor. Same pleasant structure, more or less.
Yeah, it's actually nice. It's fine. It's not quite as well.
Well, let's keep looking. I mean, there are plenty of these that end in tautology.
They all in the tautology, just
No,
I'm just incorrectly covering it.
Okay, you know what I mean.
Yeah.
Well, take your pick. I mean, that's a simpler theorem, isn't it? Wait a minute. Oh, silly me.
What?
It should be sorted by the leaf count of the first of this. Well, that's got a very pleasant tautology in it. I think that first one is fine. Okay. Okay, which of these was the most elaborate? This one here, it's not much more elaborate.
Well, some of them aren't really unfolded, so it's hard to tell.
Let's make the time constraint a little bit higher and just see if we find any bigger
Yeah,
ones. And also let's use the thing that this thing here. What did I do wrong? Yeah, oh, look. Graph. What the hell did I do wrong? Oh, there's a percent in there. This is the correct axiom system, right? So it's percent 296.
Yeah, what
What happened here?
What?
Something's horribly wrong. Oh, I bet AXX is wrong.
Okay.
Why are these so simple?
Why are they laid out like that?
Maybe they have some weird aspect ratios. Oh, look, it has a weird aspect ratio setting. That's why. But they're still comparatively simple. Well, some of these are kind of fun. Are these more complicated than what we were seeing before? Or are they the same?
It's hard to know because at least personally, because they're rendered differently.
Take largest by proof length. So that will be the longest there. So A. BBAA.
That one looks, that's hard to tell.
Well, I mean, we know that these are look, we can do, let's do it one more time with an even larger timeout.
Okay.
Hey. Well, there's a bigger one there. A, B, A, A, B, A, B, A, B. What the heck? Okay, let's just get these percent 320 and percent 319. Okay. First slash at percent 320. First slash at percent 319. All right, so let's say complement percent 321, percent 322.
Okay.
So I think there's more juice to get here. Let's do
Want to keep going?
let's do one more run. I mean, let's do one more. I mean, because that clearly has more nodes in it than this guy does by quite a lot.
Yeah.
All right, let's go. Oh, what the hell? Let's do 150. Okay. It's kind of annoying. We'll have to be sitting there, but we can start prepping the next thing. It's going to say. It doesn't show up in the first few steps, even though millions of other theorems do, but only theorem parade. It's not easy to know. Well, is it the next section by any chance? No. Discuss a little later. Allow one effectively to guess what theorems might be derivable from a given axiom system. So for example, here's a guess at a theorem. And here's a representation of its proof. Where now the length of an intermediate lemma is represented, is indicated by the size of the corresponding node. By the way, we also should make sure that these bluify to be that color. Okay, A dot B dot B. That's yet different again, isn't it? And is that still more complicated than what we had here? Well, let's just do a vertex count.
Yeah, instead of just eyeballing
320.
them. Yeah. Right.
320, let's do a vertex count. 28. Okay, so there's 4 28s there. That's really weird. There's more 28s there. Who knows? Okay, well, I consider that one fairly jolly.
Yes, yes.
And let's just see if there's
You
a
want to label
simpler-
the tokens though? Or not?
No, because they're really complicated. We'll say what
Yeah,
that
that's
one.
fine,
We'll
that's
pick
fine,
out what
that's
it
fine.
is.
Yeah,
Okay,
fine,
hold on.
fine.
Hold it. Oh, hold on.
Yeah, holding.
Okay, which is the simplest of these? These are 7, 4, and 4. They're all 4 and 4. So let's use that one. Beauty contest. Yeah, that one looks fine. Okay, find equational proof. I think the relative size of things. Is that the one we actually had? That's a different one.
It's it's not the same.
God, do you know why that is? That's because the variables in the theorem have different names. Watch this. Okay, what's going on here? I don't understand what the hell's going on here. Time constraint 50 for all ABC. Make sure that the AXX thing
I'm not sure that that is the right axis. You know.
Okay, so let's put that axiom in.
Just about right.
What the hell? Okay, so hold on. Percent 296. Okay, so percent 296. Well, let's do this one just for difference. See if that ends up being the same. What did I do wrong? I didn't. There's a paren missing again. Okay, I am totally confused. What is the difference between these? See this? I am going to do something whose insanity level is very high. Watch this.
Yeah. Okay. Okay.
Oh my God. Do you see what I see? It's different on different machines.
But it's really different.
That is the craziest thing.
Why?
Let's run it again.
It's not insane after all.
I think it might be. No.
What?
Well, final equational proof can return different results.
What makes
There's
it get
no-
a different result?
That I don't know, but I definitely seen even simple examples of that.
That it can give a. Can it be non-deterministic?
No, it's not respecting it. And I think I already reported it with my bunch of find equational proof bugs. No.
We probably should escalate that one. That's an ugly one. Okay, but anyway, so this, how many nodes are there in that guy? Because these don't look that complicated. Vertex count 22. Okay. What was the most complicated one we found here? 28 or something, right?
Yeah. Yes. Yeah. Yeah.
Oh, for goodness sake. Oh, for goodness sake. Well, I mean, so what do we have to do here? Do we have to run it again? Well, there's a different one there.
It's
A little bit more
not
complicated.
the same. It's simpler. Yeah, it's shorter.
Than this one here.
Wait, actually, it's hard to tell because the layout's a little different.
That's not much bigger than the previous graph. That looks very similar to the one above.
No, that's not good enough given what we
No,
found.
I know. So let's look for a different. For this axiom system, we were finding much jollier creatures. So let's go with this axiom system.
What?
What?
Well, after all we did with the other one.
No. We're going to change axiom systems here. We're changing horses. We're going to change it for this example.
Okay.
You see, from my point of view,
Yeah.
Sometimes, I mean, some of these things I left in NKS as I just, oh yeah, well, it's just this thing, whatever. I was kind of leaving those for the future, for somebody to find them. And like, how the hell did you get that? I used to do that when I wrote papers using, computer algebra type stuff in the 1970s. I would just have these random results. And people would
investigate.
Yeah, people would write to me and say, how on earth did you get that result?
Yeah.
And I would usually, what's that? I was like, whatever, I'm not sure I ever really gave him a tremendous amount of detail. I mean, I have to show you something.
So you were not a very forthcoming
well, I don't remember
teenage scientist then.
I don't really remember. I remember that. I'll show you something which I remember was. A good one. Let's see. there's some really, trying to remember, I think in here there were some really jolly ones.
What paper? Oh, okay.
Some old paper. What were they?
But what I never understood is, how did you proceed from whatever your school studies were to doing this kind of mathematics?
I didn't learn this stuff in school. It also isn't very hard.
No, I know you didn't learn it in school. So how did you just start?
Yeah, it's not very hard. I mean, this stuff is turns out not to be. I mean,
Yeah. So you just started doing it basically.
yeah. Look, there's an example of a fine formula that you wonder how on earth did somebody derive that?
How did you derive it?
It was a computer.
Yeah, it was a computer. Yeah, right.
But nobody's seen those kinds of things before. Those were deeply exotic. Oh yeah, look at some of these. These get more and more exotic. I think I was just showing off at that point.
So you kind of just you just manifest them without really explaining how you got them.
I just say, well, for blah blah blah, this is true. I mean, I do explain what the principle of it is, but the actual, this involves various
derivations.
kinds of higher mathematical functions and trilogarithm functions and all kinds of exotic things in the middle. But anyway, see, those are completely unsurprising now because everybody knows you can do that with a computer now. Okay.
Which is why we have to have a new computational paradigm to bewilder people now.
Well, I don't know. I think some of these graphs that we generate here bewilder us too. So for example, for the axiom system, here's a guess at a theorem. Okay, so here, this is rather jolly. Assume it doesn't collapse somehow. Yeah, that's much jollier.
That's interesting. What is the topology of a graph like this meaningful, by the way?
I have no idea.
Because
And by the way, we probably should have the tautology indicated in some special way. As a representation, like the intermediate theorem is represented by an and in this case, the longest, I'll just is. Now we're just showing off. This is a typical, look what we can do with a computer. Wait a minute, take largest by. Oh, really? Is it that way around? Wait a second. Am I confused? A function and a length.
Nick, any instincts?
What's happening here? Oh, maybe there's no vertex list there. That's the problem. Oh, it's probably equal. That's nice of John.
Yeah, it really is showing off when that's the result. That's great. Now wait. For click to copy, wouldn't it be better to actually include the computation you actually just did?
Yeah, okay, fine.
See, that's the difference, right? Your Caltech papers didn't have click to copy.
That's true. That is true. That is a big difference.
Though it's a big difference only for the people who actually bother to
Click.
inspect, but you have to click. Do you have data on that, by the way? Do you know how many people
I'm
are
sure we
using click
do.
to copy?
Sure we do.
That would be interested. I mean, I'd be interested in seeing that.
No.
Like the most popular C2C item.
Okay. Now we got to talk about the fact that some of these involve by substitution. Okay.
Have we discussed critical pairs yet?
No.
Is now the time?
Yeah.
Yeah. Okay.
One feature. Okay, we got to explain a couple of things. We've got to explain why it's a good thing to go to we got to explain why the okay. We got the couple of things we're going to do. We're going to explain why there are by substitution things here. Then we've got to explain, okay, whoops, why by substitution. Then confluence. Then why evolved to tautologies.
Yes.
And then we might talk about proofs among proofs. Just a comment about proofs among proofs.
Proofs among proofs.
Transforming one proof to another proof.
Yeah. But that's discussed elsewhere. No?
No, it isn't.
It should be, something should be mentioned in the motion section. Because that's what motion is.
Yeah. Okay, now this is a fairly minimal example of a, I mean, we've got much better examples of by substitution up here. Not sure that we need a minimal example. I don't think we're going to give a minimal example by substitution.
No, we've already
Yeah.
had a whole section on by substitution, and the reader can see it in the examples we've just shown.
Yeah. Um, we really need to update find equational proof for 13.1 to produce pictures that look like this because they're so much nicer looking.
Yeah. Yes, yes, yes. Probably after we finish this project, though, right?
Yes, but it's something for the list.
It's something for the list. The ever longer, things to do after we finish the MetaMath project list.
Yes. Okay. Oh, we also got cut elimination. We also got to mention cut elimination.
Well, Nick, I think this is going to be your time to shine because these are many concepts that you've helped to.
Okay, so let's
To
talk
introduce
about.
here,
So
so-
what do we think? Should we mention? Should we mention by substitution immediately?
Why not?
Or should we talk about, okay, what's the relevance of confluence to these pictures?
Well, this is where the matter of completions comes in.
Yes.
But I think that critical pairs, Nick, unless you would disagree, aren't critical pairs easier to describe than completions?
No, you know what I think we should do? I think we should say here, how does automated theorem proving manage to it's worth discussing. Well, okay, wait a minute. In principle, it's possible to turn around, to rearrange results from automated theorem proving, graphs from automated theorem proving, token event graphs from automated theorem proving to have the same structure as the ones we fish out of the entailment cone. With axioms at the beginning and the theorem being proved at the end. Arranged token event graphs. Arranged token event graphs generated. Have the same structure as the ones we fish out of directly. in which, in principle, it's possible to rearrange the token event graphs, if they're improving, to have the same structure as the ones we get directly from the entailment cone, i.e., but typical strategies for automated theorem proving but typical strategies for automated theorem proving don't naturally produce such graphs. In principle, automated theorem proving could work Okay, wait a minute. In principle, automated theorem could work by searching directly for a path that leads to the theorem one's trying to prove. But it turns out to usually be much easier instead to have as the quotes target um, usually turns out much easier instead to have as the target a simple tautology. In effect, the reason is that one can the reason is that this helps. In effect, the reason is that this helps in being able to have a simple tautology. In effect, the reason is But usually it's much easier instead to have as the target a simple tautology. In effect, the reason is that then there's a well, it's like an energy function, right?
Objective function.
Right. Is that then there's a and there's a more definite objective function that can be progressively sought. Nick, is this even vaguely reasonable?
A little bit.
What?
A little.
Explain how you would explain this.
Well, there's well, don't understand it completely myself. It's like there's some kind of ordering function on your terms. That's the one thing. And then you just apply this reduction selection function or whatever how you call it. And just hope for the best. I don't know.
Yeah, by directly searching for a path. But usually it's much easier instead to have as a target a simple tautology. And in fact, the reason is that then so this makes it this gives one something closer I'm going to change the wording in a minute. And the reason is that I think I have a reasonable way to say this. In fact, the reason is that this lets one gives one a simpler, quote, subjective function criterion for deciding for ordering reason for this is that in effect the reason is that this gives one, what do I say about this in NKS? I think I said something about this actually, and let me look in the two. There's another place I wrote about this. Here. Oh, God. Okay. Oh, for goodness sake. I can't even remember this mnemonic here. Bit by bit, a program computed Boolean algebra's best binary axiom covering all cases. I think I just better memorize this thing. Okay. Okay, this is exactly the all right. Okay. So in effect, the reason is that this gives one something closer to a definite objective function that lets one decide which branches to try in reaching the target. But how but how should one go sometimes one wants to just make a substitution in but an important idea they're using the original axiom or another lemma one's derived. An important idea automated theorem proving. Are critical pair lemmas. In which can be thought of. Important idea in automated theorem proving, which are often thought of as lemmas that combine pairs of other lemmas. In our setup, however, critical pair lemmas just correspond to bi-substitution events. As indicated.
Okay.
Combine pairs of other lemmas in our setup, however. So we have to say something about confluence. We have to say that
Yeah, well, that's another matter. I mean, it's related, but now we get into things like completions.
well, but this is okay. In typical automated theorem proving, in automated theorem proving, it's common to have to pick a particular branch, to want to pick a particular branch to pursue. There are some systems, however, and one of the big issues is whether such a branch can end up going astray and never reaching the target. Systems One of the biggest is whether such a branch can end up going astray and never reaching the target, or whether it will always eventually merge with other branches to reach the target, have the property that every branch will eventually merge. And this is related to the property of causal invariance, which is important. That is important. Now, you're going to tell me why the systems we're looking at, why cumulative systems are always confluent.
Nick, take it away.
I'm thinking, well, how can you explain it?
Well, you've had a nice explanation in
Just a
terms of
second.
completion.
Well, the well, by
I'll be right
definition.
back. I'll be right back. And then
Okay,
you can.
okay.
You've
on
bought,
the-
yeah, you've bought Nick some time.
Saved. Okay, let's think about it. Well, there's time. What else?
Hi.
All right, Nick.
It's obvious.
Great.
You and GH Hardy. Okay.
Well, seriously though. Okay, let's step back. So the confluence means when we branch, basically where do we merge? In our case, our statements branching. So we have an event that produces more than one statement, right?
Mhm.
And confluence means that later in our evolution, those statements can produce the same one. It's like they have a common descendant, something like that. And you can
In the multi-way graph.
or in the token event graph. It doesn't matter. It doesn't matter.
Yeah. Okay, but this is only a fragment of the token event graph. This thing here is just a fragment. In fact, I said somewhere here. This is again a fragment of it, a fragment of a token event graph.
Come up with a better term for it. What is it exactly? I mean, a fragment just sounds. It's not quite right. I mean, it's a piece of the entailment cone, but it's an important piece.
Well, we could say a graph made with tokens and events.
No comment. No, wait. Nick was explaining something.
Oh, I know, but I want to get this right here. Subgraph the entailment cone. Is it a token event graph when it's so incomplete? So I'm saying we call it a token event
Is-
subgraph.
Sure,
What's that?
sure. I think you can say token event graph is just a graph with tokens and events.
Yeah, it is a token event graph.
All right, okay.
It doesn't have to be complete in some
Okay.
sense.
Okay. Now explain.
Confluence?
Yeah.
Well, yeah. So after our statements branched, the fact that they always converge, meaning that they have a common descendant, is just follows from the fact that we can create new statements by just combining some rules, right? Maybe we even combine them themselves, right? Because any statement is a rule, so we can combine them by substitution or substitution. Means that we just create a common descendant just by combining them. So just in this sense, it's confluent in very trivially.
I see. In the full, I'm getting it. Okay. Okay.
Every event takes 2 tokens.
I know, but we're not looking at. We're looking at the full token event graph, the full entailment graph. And we're asking this question about it. It's not true of these individual ones. This is the output. See what I'm saying? Within this graph, you don't see this anymore. Okay, so the point is that in the entailment graph, in the entailment cone, entailment graph, there is branching, right?
Yep.
But the whole point is, okay, so
Well, actually, there can be a case when two statements can combine and produce a new statement. That would be it's like an empty output event. So would that be considered confluent? I don't think so. Right?
yeah. Well, hold on. Could work bidirectly. It's just much easier. Set up a target. At some level, what am I theorem proving? Still try to navigate through what amounts to the through must still, at least conceptually, at least conceptually, what must still try to navigate through the entailment graph through the full token event graph in the entailment cone and the main issue in doing this is that there are many branches there are many places where one does not know, many places where one does not know which branch to take.
Now,
Yes.
this is going to sound picky, but I'm not exactly sure what the phrase, the token event in the entailment cone, what exactly that means. I mean, it is the entailment cone.
That makes up the entailment cone.
Yeah,
What
okay.
we're talking about.
better. Okay, cool.
The main issue in doing this is that there are many places where one does not know which branch to take. However, a critical fact, however, is that ultimately, and at least so long as at least so long as one is using full by substitution, I hate to say a critical fact about critical pair lemmas.
A key fact, important fact.
There are many places where one does not know which branch to take.
Crucial
The crucial
fact.
point, however,
Yeah.
what's crucial, however, but here, there's a crucial, if at first surprising, fact. At least so long as one is using full by substitution, it ultimately doesn't matter what branch one takes. Because there'll always be a way to merge back to wherever a different branch would have gone. Merge back. Doesn't matter what branch one takes because there'll always be a way to merge back to any other branch. Merge back to any other branch. But here's the crucial first surprising fact. At least so long as one is using full by substitution, it ultimately doesn't matter which branch one takes. There'll always be a way to merge back to any other branch. This is a consequence of the fact that the accumulative systems we're using automatically have the property of confluence, or rules correspond to essentially the reason is that given any two statements given two statements on two different branches, there'll always be a by substitution that will merge. There'll always be a way that will merge these statements into a single statement. Substitution alone isn't enough to achieve this. Tell me why by substitution is.
What do you think substitution is not enough?
Because it isn't a critical pair lemma. You can't get all critical pair lemmas.
But maybe you still can like reverse it. Because all your previous statements are available. You can just pick up the same rule but in reverse order and substitute back and follow a different branch. It's like,
But that's just reversing an edge.
but it's still true, right? Because all our edges are reversible. The confluence follows from that.
From what? From the reversibility of the edges?
Yeah.
Are you sure?
Oh, look, if you have a branch.
Yeah,
you
it's
can
obvious you can go back.
Climb up. Yeah.
But isn't there more to it when there's by substitution? You can make progress with by substitution. I might have to have the automatically have the property of confluence that every branch is accompanied by a subsequent merge. There's a trivial sense, there's an almost trivial sense in which this is true. There's an almost trivial sense of that's the property of confluence, which says that every branch with by subsequent merge. There's an almost trivial sense, there's an almost trivial way in which this is true. By virtue, there's an almost trivial, this is true by virtue of the fact that every edge that for every edge there's ultimately a reversal, that for every edge there's also the reversal of that edge. Also, there's also a reversal of that edge. For every edge, system also includes reverse of that edge. But there's a more sophisticated, but in addition, given two statements, but there's a more substantial reason as well. That given any two statements on two different branches, there's always a by substitution It's always a way to combine them using a by substitution to get a single, get at least one, to combine them. There's always a way to combine them using a by substitution to get a single statement. Okay, so in our physics project, the concept of causal invariance, which effectively generalizes confluence, is what leads to maybe this should be in the relativity section. Is it relevant to the reference frames business? It has to be.
It should be. Yes.
What are we going to say about that? What section is that now in?
It's near the end, isn't it? Okay, so somewhat near the end.
Doesn't matter in what order you prove the theorems, you'll always get the same math in the end. There's a more substantial version, but there's a more substantial statement as well. The more substantial. There's a more substantial later, a physics project, the concept of causal invariance, which effectively is an important one that leads, among other things, to the concept of relativity, leads, among other things, to the idea of relativistic invariance. Later on, we'll discuss the concept, the idea and its relationship to causal invariance and to notion of relativity in mathematics. But for now, the importance of confluence is that it simplifies automated theorem proving. Because, in effect, it says one can never ultimately make a wrong turn in getting to with our setup, basically this is something that is manifestly true of the entailment cone. Because in effect, it says one can never ultimately make a wrong turn in going to a particular theorem. The path one takes may be long,
Okay. Yeah.
but maybe overly long, but eventually it will be able, well, ultimately make a wrong turn. Or alternatively, that every path eventually gets everywhere. Or alternatively, that if one keeps going long enough, every path will eventually get everywhere, go everywhere, reach every theorem. In a sense, though, this is exactly what happens in the entailment code. And the question is, okay, why do we need critical pair lemmas here? Exactly what happens in the full entailment cone. So in fact, it says one can never ultimately make a wrong turn, or alternatively, if one keeps going long enough, every path will eventually. In a sense, and indeed, this is what happens. So it simplifies automated theorem proving. And indeed, this is just how things work. For now, the importance of confluence. Indeed, this is exactly how things work in the full entailment cone. But in trying to put the challenge in automated theorem proving is to generate only a tiny piece, only a tiny part of the entailment cone. Yet still get to the theorem we want. And in doing this, yet still and in doing this, we have to carefully choose which branches we should try to merge using by substitution events. In automated theorem proving, these by substitution events are typically called critical pair lemmas. And there are a variety of strategies for enumerating, for picking critical pair lemmas. A variety of strategies for defining an order in which critical pair lemmas should be tried. Okay, what else do we have to say here? Other than that, you know, if you've understood it so far, amazing.
Well, cut elimination.
What's that? Cut elimination. I know. We have to talk about that.
Well, Nick, what do you think?
No, hold on. I got one more thing here.
Okay.
I want to bring this back. I want to basically say the results are incomprehensible. Let's see, because I want to bring this back to why is this relevant to everything we're talking about. It's worth realizing that in the end, and then there's no So that's realizing in practice, what do I want to say? I want to say in practice, we haven't a clue whether it finds the shortest path. And there are a bunch of heuristics you can imagine trying.
Okay.
Okay.
Yeah.
Are there it's worth pointing out that there's absolutely no guarantee that such procedures will find the shortest proof of any given theorem, or in fact, that they'll find a proof at all in a given number of, with a given amount of computational effort. I can imagine I can imagine higher order proofs in which one attempts to transform a given proof using which one attempts to transform not just statements of the form LHS equals RHS, but full proofs. One can imagine using such transformations to try to simplify proofs. proofs, say, represented as token event graphs. But one feature of automated, but one general, but regardless of this, but it's worth but I said it's worth pointing out. But in a sense, all of this is very, quotes, non-human. Mathematics. Well, how to say this? I mean, we're basically saying that what are we saying? The coarse graining
Which aspect of this is non-human?
the fact that this is incomprehensible gunk that comes out.
Okay, I thought you were addressing specifically this last paragraph.
No, I wasn't.
Well then, yeah, so it's confusing. I thought you meant that the translation between proofs is not human, but that's not true.
No, it's not true.
Even though there are limits to translation between proof according to the computational bounds on the observer, and that's where things like that destructive interference will come to the fore.
Yes.
It seems like I don't know.
Okay, I think we want to say a general feature of automated theorem proving is that its results tend to be very, quotes, non-human. Yes, it can successfully demonstrate it can provide incontrovertible
Well, yeah, just the
evidence that a theorem is valid, but that evidence is typically far away from being anything like a narrative, from being any kind of, quotes, narrative suitable for human consumption.
Now, okay, but there must be a bigger point here. Because a
Yes.
key question that informs much of this is this relationship between, say, the fluid and the molecular dynamics
I know.
of math formalization.
Right.
So
Typically
there's a
far away.
real
Yeah, right.
punchline.
Yeah, I know.
here.
There's a punchline coming. Yet it can provide, yes, it can provide income, but the evidence is typically far away from any kind of narrative suitable for human consumption. In the analogies we've been making to an automated proof, what's an itinerary? What's a turn by turn? Represents, gives detailed turn by turn instructions.
Iterated?
No, I'm thinking like a GPS.
Oh, okay, okay. It's not clear though.
I know, it may get clearer.
Actually, I think you're mixing metaphors now, right? We're talking about molecular dynamics, or are we talking about GPS? Because they're pretty different.
No, they're not. No, they're not. Those are GPS for molecular dynamics. That's what I'm trying to say here. Okay, but that evidence.
No, why do it like that? I mean, you've already set up this metaphor. Why?
Oh, because you'll see.
Okay, all right. Let's see.
Not as hopeless. Okay, that evidence is typically far away from being any kind of narrative suitable for human consumption. Automated proof. Um, right, but wait a minute. But this is but gives no useful information about Okay, the basic point is, rather than describing an overall fluid motion, rather than doing how molecules in bulk in other words, you can find out that this individual molecule can get there, but the other way to find that out is to figure out that there's a giant flow of fluid in that direction, one consequence of which is that that individual molecule gets moved there. Does that make sense?
Hold on. Hold on. Hold on. One more time.
Okay, so the idea is, this is operating, saying you can move a molecule from this place to this place.
Mhm.
Okay, the other
Mhm.
idea is that there's a vortex, a tornado, whatever else, that's moving lots of molecules.
Sure.
And it's kind of a more
Yes.
human level way to describe how the molecule gets from here to there.
Sure. Bulk, kind of just bulk dynamics. Absolutely.
Yeah, right.
Yeah.
Gives detailed term how a molecule can reach a certain place in a gas. While higher level mathematics, while human level mathematics, higher level human style mathematics talks about how a fluid overall motion in a fluid talks about overall motion of fluid Okay, let's clean this up. Yeah, that evidence is typically far away from being any kind of narrative suitable for analogy to molecular dynamics. An automated proof gives detailed 10x10 instructions that show how a molecule can reach a certain place in a gas. On the other hand, talks about overall motion of fluid and uses this in a fluid talks about overall motion of fluid explaining, thereby explaining overall motion of fluid. Talks about how molecules get to where they get to through human style mathematics, on the other hand, operates at a higher level, analogous to talking typical. Okay, hold on. Operates on a higher level. What point am I trying to make here? I'm trying to,
Well, can I ask something?
yeah,
You see, there's another aspect to the punchline here, which is, okay, on the one hand, we have this perfectly valid dichotomy between automated theorem proving and, you know, uh, mathematics as practiced by working mathematicians. But where do we fit in? That's like the
yeah,
key punchline. Where does this framework fit in?
I know. But the evidence, analogy to molecular dynamics that show how molecule and it's the fact that such higher level mathematics is possible, that is a core part of what our physicalization mathematics a core part of what's achieved by our physicalization of mathematics is understanding why this higher level is not quite right. I mean, basically, what is the point here? So we need to talk about cut elimination. Maybe we should talk about it before we get to this wrap up.
Well, of course.
Okay, let's do it here.
You don't want to be the follow-up act to something like this.
Right. I can imagine using such to try to simplify proofs.
But wait, don't you want to finish this thought before you go to cut elimination?
No, because I'm going to be clearer when I come back to it.
Okay.
One feature do we have an example of cut elimination? Can we do cut elimination for something?
Yeah.
Yeah.
Can you
For
show me an
every,
example?
it's find replace path function. So any proof object can be cut eliminated.
Okay, give me one. That one is probably not a candidate. Do you agree? I mean, isn't that insane?
No.
It'll be exponentially larger, won't it?
Well, not necessarily exponential.
All right, let's try cut elimination for this guy, for example. Should we try that or just?
Well, Nick, what do you think? Is that?
Yeah, we can try it.
Yeah. Okay.
I'm not gonna guarantee that it's gonna work. It's still
Okay.
it still fails for some cases.
Is it in code 1, Nick?
No, it's like a separate function in non-ready.
Not
Find
really.
replace path.
You know, this is a complicated project. In case you didn't notice that already. Sometimes projects are simpler than you expect. Some of these application areas, like immunology, might be.
It's going to be terribly complicated.
Why do you say that?
Immunology, it'll be complicated, but we'll know when we succeeded, which is always helpful for a project.
Hmm. Well, anyway, okay. I mean, I'd like to, but one thing I want to put into the empirical metamathematics section here is, so what experiment could one do that would be kind of demonstrate physicalization of mathematics? I think I've talked about that in some other sections, actually. I've talked about the fact that usually, in physics, it's not trivial to drill down to see, the atoms
Sure.
of space. But here we already have them. I think I already talked about that. Okay, cut elimination. What do we do here? Nick, what do we do?
Take your proof object and find replace path.
Okay, that's my proof object. Now what do I do?
Well, find the function in non-ready.
I found it. Find replace
Then-
path.
Then just run. It's a single argument. Takes your proof.
This?
Yeah.
What the hell is that?
A bunch of meta information.
Okay, so
There's
what
a
do I
path.
now?
You can ask for a path.
Okay, but then
It'd be nice to have some way of representing this.
but what the hell is this?
It's a single
It's
path.
just a sequence of replacements or rewrites. That
Okay, which are substitutions.
Yeah, could we show this as a TEG? I don't know if that would look good though. It would just be like
That's a straight line.
it'd just be a straight line.
they're not always substitutions.
How should this be represented? Because it's going to just be a straight line. What's a nice way of illustrating?
Well, just like we had this column, with frames. With
Yeah,
dashed lines,
right.
like that.
But I think to show this, look, we should show a simpler case. And we should show,
How about that
is
one?
that case going to be non-trivial?
Well, let's look. Let's see.
Well, that's not even there. What do we want to do? We want to do this one here.
Now this is just token graph. You have to convert it into a proof object.
I did. I know I'm going to do that. I say
No,
quotes.
I know. I mean, I have a function that converts token graphs to proof objects. Maybe it will even work here. I wonder.
Okay, so in this case, what's happened is that we're not reusing anything in this case. We need a slightly more complicated case to show reuse. Right, not as complicated as this. Okay. A feature of the proofs we've been showing a general feature of the proofs we've been showing is that they are accumulative. In the sense that they in the sense that they introduce lemmas which are then reused, which can then be reused, is that they continually introduce lemmas which are then reused. But in principle, any proof can be unrolled into one that just repeatedly uses the original axioms. Without introducing intermediate lemmas.
It also uses novelty generation.
No what?
It also performs just usual substitutions when you can replace a variable with some expression.
Yes, but in principle, any proof into one that just repeatedly uses the original axioms. Does substitutions with the original axioms and never introduces other lemmas. The necessary so-called cut elimination can introduce exponential complexity into the proof as each with what used to be intermediate lemmas always, what's the right word? What do you do? Always, quotes, getting recalculated. With the I was introduced complexity necessary and introduce unrolled into one that just repeatedly does substitutions. Just repeatedly uses the original axioms, never introduces other lemmas. In fact, purely by substitution. Effectively be done by always recreating each lemma from the axioms whenever it's needed. A process which can become exponentially complex. as an example, consider the proof based on the axiom proof can be unrolled this proof involves reusing several lemmas, but it can be unrolled into an equivalence proof. Okay, let's do it. Okay. So what's a good example here? Let's pick, what do we have from that fairly simple, where are we going to have something that has a bit of reuse? Show me something with a bit of reuse. How much reuse do we want?
I don't know. No, those proofs rarely actually do reuse,
Yeah,
in my
right.
experience. Axioms getting reused often, but not dilemmas.
Right.
Well, in more complicated cases, plenty of lemmas get reused.
Let's see. Anything here?
What about that one?
That's yeah. Okay.
I don't know if they get reused. You know, I have to say, I think there's something about sort of energy that has to do with lemma reuse.
Yes.
I don't know whether we've talked about that very much.
No, we haven't. I don't think we have.
Oh, God. And that also relates to causal stuff.
Causal, yeah, I know, right? We need a causal graph to look at the flux of causal edges.
Lemma reuse and causal graphs. We're getting to the end. We're getting to the end here. This is not an infinite process.
No, no.
Okay. Where do we?
We just want an example of reuse.
Yeah, we want an example of reuse that isn't one of these crazy things.
Too much. Too much. Right?
I think
Oh,
so.
Maybe a modest one in this batch.
This one is nice.
What's that?
This one is nice too. It's like one lemma was reused 5 times there.
This one here?
Yeah, like the token, you see, the reuse is when the token has multiple output edges. That A equals BA got reused 5 times there.
Okay, well, can we find another example where that happens?
What, you want it smaller?
Well, what about this guy here? Was that the original axiom?
Yes.
It's the original.
Okay, so here, well, look, the problem here is that we evaluated these let's do this. Let's get this axiom. This is take largest by. See what I'm saying? So we don't really want the largest.
That's what I was saying. We should look at another one in this batch, like one near the end, right? Yeah, maybe one of these. Be a little smaller. It's not too big. I mean, it's not tiny.
It's not tiny.
There are some examples of reuse.
Well, let's
Recycle.
just look for things with large integree. Let's just look for cases where there's lots of integree.
Out degree.
Out degree.
Okay, so let's go.
Well, there's some out degree here in this last one here.
I know, but I think we can get a slightly simpler case. Okay, so let's do this. Take largest by, and instead of proof length here, okay, what we want to do is take this proof object to token event graph, okay, and do the take largest by. Let's not do the take largest by here. Let me just put this in a different section. Okay. So now let's take out the take largest by. Okay, now for that whole thing, we will say, oh God, what's the percent here? Take largest by the out degree of those things. But what was percent there? That was this. Now we could, should we just take random ones of these?
Mm,
Okay, well, anyway, let's do this. Okay, 3,000 of those guys. Okay, so take largest by. In this, we want the out degree right? We want, is it the max out degree?
yes. For a token. Yeah.
For a token or for anything in the graph?
For token.
Token.
Max out degree. Vertex out degree of hash 2. No, of hash sub 2. Okay, that's the graph. Oh, but we have to do that by we could do it for the whole graph. Is it enough to do it for the whole graph? Let's just do
No,
it for the whole graph. What's that?
Well, you have to specify tokens.
Okay, well, how do we do that? For
Well,
vertex
well,
B.
maybe that it doesn't matter because those events are always have one out degree, right? The
I
events.
think so. Yeah, I think so. So I think this is enough. Do you think this is right?
We'll test it out first.
Well, and then you'll guess.
Well, machines are dropping like flies here.
Mhm.
I should have put the thing to token event graph in the inside of the parallel map. Is that very time consuming, the proof to token event graph?
Proof to token? No, not really.
You want to make your guess yet, Nick?
About what?
Whether the code is right.
Well, I have a bad
chance.
feeling about. Yeah.
Okay, so let's just do it for
This is bad. Oh,
No.
there's a big out degree.
7.
But is that the original axiom? No, it's not.
Mhm. Okay, can we use that one?
Probably. Yeah, let's try using this one.
Great.
Okay, what do we do with this? We take that graph. No, we don't take that graph. We take this thing here. Then we take what the hell is that?
that's fine.
Okay, so now what I want to draw is an analog of a token event graph that just shows a bunch of yellow things.
Just the path.
Goes, yeah, it just shows the path. With the axiom coming in, it just wants to be a feeder like this. How do we do that? Do you get what I'm saying? Just the axiom is the feeder for all of them.
Yeah. What do you want? You want to visualization of that or
Yes, yes.
different from that one?
Which one?
to
Oh,
the
look,
token
look.
when
Well, with find replace path, we just have a single path, right? So that would be a
Yes.
novel representation. We haven't seen that before. That's what we want to see.
Okay, so that's my original one there. Okay, so now what we want to do is to show this as a bunch of yellow feeders like this. See what I'm saying?
okay, so you want to make a path and then turn it into the same looking token on graph.
Yes.
Okay.
But I mean, at the very least, let's do symbolify patterns of %15. And then let's now say a path graph of
Just
that.
then they're not gonna look like equalities. No, it's okay. That's
Well,
the
how
point.
do we make them to?
Well, maybe you like partition it first, partition to one of this list,
Okay.
and make equalities. That.
Like this.
Yeah. And now we can make a path graph, and then just add this kind of
But
key.
why? Hold on a second. That first thing there is nothing to do with any equality that I've seen before.
Some kind of, it's a substitution lemma. It's in between one.
But how do I see that this is? I want to see how the proof works from this. How do I see the proof from this path?
So if you can see an explicit rewrite, you can ask find replace path. There's like a function. How do we go from one step to another, from one expression to another?
No, I understand that. I'm not asking that question. I'm asking the question, what? How do I see something that goes from this hypothesis, the proving of that? Where is that hypothesis even in here? So I'm
Oh, you
asking.
can, I get it. You can rotate it then. Basically, your path can be rotated, right?
Okay, well, where is it even in the rotated graph?
No,
A, B,
not
B.
not the one before doing partition. If you just take the raw path, that would be just a sequence of expressions where the first one is the left-hand side of your hypothesis and the last one is the right-hand side. If you want to make it into equality, then you rotate it and then do your partition. And then you're going to have a hypothesis on some side.
Let me rotate it right. Okay. Okay, that was A. It's not the same thing.
Make sure, show me the
A, B. Oh, no, it is the same thing.
okay.
It is the same thing. It is the same thing. It's all good. It is the same thing.
Yeah, just sort it. Okay.
Okay, so now what you're saying is, where do I see the result here? How do I see that this is transforming into a tautology?
Well, I dropped the tautology. You can make like tautology anywhere, right? You just pick any expression and make it into a tautology.
No, I understand that, but you've got to do
Basically
this by substitutions. I mean, each one from each step to the next.
But yeah. It's like pick. So you have a path, right? A sequence of rewrites.
That's
If
this.
yeah, no, without equalities. It's just okay. For these equalities, only one side changes. I think you always change the right hand side, right?
Yes.
Just by construction.
Yes.
Then if you want to make a tautology, just pick any and just any right hand side.
Okay,
And repeat it.
Look. What we're trying to do is show that you can get to this thing, right? This is making a proof. What I want to show is that this hypothesis can turn into a tautology with some sequence of rewrites. If you tell me I can get a tautology anywhere, it's not going to help me. So I'm saying it's got to be a certain set of rewrites that turn this into a tautology, just like a certain set of rewrites with shared lemmas turns it into a tautology here.
Okay.
Am I making sense?
So, but okay, the plan was to make a staircase proof, right? As you have on the left.
Yes. Right.
So I don't understand if you have now you have a sequence of equalities there that we constructed, with the first one being your hypothesis.
Yes.
So, and then to make it into this staircase, you just add your axiom, right? And make a tautology from the last equality, basically. In that sequence that you have.
Yeah, I understand.
Tautology from the last one. And then,
But it doesn't, but it has to actually make the tautology. Otherwise it hasn't proved anything.
But well, that's what it's doing. So like you're rewriting, because the last expression you came up with it with your last substitution on the right hand side.
This one here.
Yes.
Okay. Then what happens next? Then you say that what you've got next is you can replace A dot B.
Wait, I don't understand what's wrong with this. I mean, the point is, as we've discussed before, you have your axiom, you have your hypothesis when you're using fine equational proof, and it's convenient in terms of the objective function or what have you to yield this tautology. But if we're just doing it as a straight path, it seems as though it's completely different. Now, you have this tautology because it's a result not of a straight path, right? Because you have your axioms and you have your hypothesis. So now we just have a path between the two of them. I don't see what's wrong with that.
Well, but do we? In this case here, maybe we do. Maybe that's exactly what we want. All right, okay, so hold on. So I think that's right. Well, it's the same axiom we were just using. Use the axiom we discussed above. As an example, the axiom above generates, from the axiom above, we can generate the proof. where the first lemma at the top, where, for example, is reused 1, 2, 3, 4, 5 times. But now, by cut elimination, we can unroll this whole proof into a sequence of substitution transformations, into a sequence of substitutions of expressions, into a sequence of substitutions on expressions done using the original axiom.
Right.
Okay, now here, my God. Well, this isn't going to be quite right, but what did I just do there? Oh, here. Go. Okay, that's using multi-way function system, all kinds of crazy things. All I want is that framery. I just want this. What the hell is B doing there? Really?
Yeah.
Okay, hold on. But where's %15?
That was the original B copy tautology.
Okay. Hackaroo. I have the correct precedence. And by causal elimination, unroll the whole proof into a sequence of substitutions on expressions. Sequence of substitutions. Done using the original axiom. But now by causal elimination, we can unroll this whole proof into a sequence of substitutions on expressions done using the original axiom. And we see that our final theorem is the statement that the beginning of the sequence is equivalent to the end, that the first well, for example, okay, but now by causal elimination, we can unroll this whole proof. Straight line sequence of substitutions. Go ahead.
That proof can be simplified just because of that B in the middle. I guess.
For what?
Because you can replace P with anything, right?
Yes.
It's
So
we can
so
just
we could
drop everything. You can just drop everything after B. Just replace B with whatever you are proving, your right hand side.
So this isn't a great example. Or is it always going to happen that
Yeah,
way?
right. How often do we encounter this? Is it every time? Well, is it every time that the tautology has only one argument on each side?
What happens? I've never seen this. I mean, what happens if I do this on, okay, hold on.
I think it's because it's like your hypothesis on the top. Like usually it's like right at the bottom where it just combines and gets your tautology.
Yeah.
With the last lemma, but now you have like an opportunity. That's why it's like your B is in the middle. So
Well, okay, so how do we get an example where that isn't the case? Let's pick a random other one of these. Let's pick this one here. What the hell is that?
broke.
Ouch.
Okay, let's go back up here.
Those are some crazy examples. I need to debug. Nice material for debugging.
Yes, but let's find a non-crazy example. Let's just try the second one of these. Or is that all fanning out from the original. No, not quite. I kind of like that one. Let's try that one. Well, that's definitely not a happy camper.
Oh, you got lucky with the first one.
Let's take %13. Okay, so let's go ahead and do this. Do I need to do this in parallel? Maybe I do. That is a very weird looking error, don't you think?
I've never seen that before.
Is it because you made a traditional form out of it?
That's possible.
What's going on?
Well, nothing is working now.
No, can you run find replace path? Because I have some cache in there. Maybe.
Should I clear find replace path?
I think it has a clear somewhere.
What the hell is that? I think I should quit the kernel here. Do you agree? Looks hopeless here. Something's corrupted. Okay, so do I just need find replace path, or I'm going to need a bunch of other stuff? I'm going to need code 01. Really? We're getting closer, guys. Sections are dropping
Yeah.
like flies, except for this one. Why
Oh,
the beep?
we're almost done. We're almost done.
I love the optimism.
I mean, you know, unless we think of something else to do, it's really up to us.
I know, but just hold on a second. Let me just find.
Are there any other major, any sections that require major content generation still?
There's some minor content generation, and there may be some bumps.
Well, that we can handle. Bumpy minor generation is fine.
Don't count on it. I mean,
No, of
it's
course, it'll
possible
be fine.
because we
What
can.
do you mean? Of course, right? I mean, it might take a couple of days at the most, but we're
Yeah,
almost
I know,
done.
I understand. I understand. Okay, let's go here. Did I do something really straightforwardly wrong here? I think I did. I think there's something just simple wrong with this thing here. Okay, find equational proof. What is it? Wolfram Physics meta mathematics. Is that right?
Yep. Perfect.
Okay.
Yeah.
Something's gone very wrong here. Is this the correct axiom to be using?
So can you first generate all the proof objects? Separately.
Yes. Okay, there are the proof objects. Okay, now, why don't I go ahead and say,
Can you,
find replace path, yeah?
can you run this first? And maybe rerun find replace path notebook. Initialization cells. Just in case.
Okay, find replace path. And then what I want to do is I want to say parallel map. Well, maybe I shouldn't do that. I should just say find replace path slash at take %7,5.
Just take any proof object like separately first. Just don't run all of them together. Maybe disable the cache again because maybe you enabled it again, just in case.
That's really weird. This was working just fine before, wasn't it? Okay, let's one iteration here. Let's just restart everything. Okay.
Okay.
Okay. Well, that example in your draft of it, does it work? Is it working?
Maybe.
Maybe it's just we got lucky and we just picked the only one working
mm,
theorem. Yes,
what?
looks like it.
What? Wait. Get.
Okay. So we need another example.
Yeah.
Okay. Let's So it's going to be one of these. Just don't know which one. Okay, but before we forget how all these work, we should okay, so let's just try and write the wrap here, and then we should go. What I wanted to do when we've done this, I want to see my Boolean algebra thing. There should be just a straight line proof of it. I think I've been looking for that for ages.
Let's do it. Okay, so let's restart and see if any others work. And let's try your axioms.
No. We've discovered that this is the only one that works. The chance that my axioms work is incredibly low.
Yeah, but the chance that we happen to pick the only one that works also seems kind of low. Doesn't that strike you as weird?
Mildly, but it had one error message. We can count the different numbers of error messages, and also the fact that it's building up a cache means it might not even work again. That's a very bizarre result there. Okay, let's do this. %7. What the hell? What's that? Take false, comma 5. No, this is much more bizarre than that.
Why %7 is false?
Oh, there's another %7 here. Okay. Okay, so now PMO. Okay, so some of these are very, very, very dead. Okay, so let's just do.
Or if you ask all instead of path, you can at least check for tests there, because it includes tests.
What kind of tests?
Like path is reproducible using function and so on.
Well, let's not bother, because we're just gonna. I just want to see whether we can find one that works. This is not encouraging. It's not even coming up with it. That's interesting. Oh, so there are a bunch that do work here. And there are some that don't.
Yeah.
Just a minute. If not free Q hash comma or failure, otherwise hash.
Exactly 60% working out of those.
There.
Right. So it's not just the one that we picked.
Yeah.
No, that would be, that's just too improbable.
Yeah, we got a good chance, 60%.
Oh no, this is wrong. This is not what I wanted at all. Oh God, this is a horrible mess. How do I find out whether the only heads are the whatever it is, the fickle, the small circle?
Sorry, what was that? I got a little distracted by the that description.
How do I find out if there's any other crud in it? How do I find this out? That's crazy. How do I find out whether this thing has, well, I want to know whether it has a failure object in it. If not free Q, hash, comma, oh, maybe non-unifiable is a string. Is it? Okay, here we go. All right, so there's some lovely ones here.
Wait, there's one that ends in B. That's interesting.
There's a
That
lot
one-
that have B's in the middle. which I
Yeah,
don't like.
the one that you had your
Let's,
cursor
hold
over.
on, let's just figure out this one here,
Yeah, that one's
first to last. So what we want to do, okay, so this one here looks like it's somewhat civilized.
Yeah, looks fine. I mean, many of them do. Are there any other criteria?
Oh, this is kind of a fun one.
Yeah.
I think that one is my favorite.
Why?
Because it just looks complicated, which is what we're trying to get.
Well, okay.
Or maybe this one is good because that's not quite as long.
Great.
All right, now let's see what it does.
It's not bad.
Oh, there's nothing particularly wrong with this one. I mean, I prefer that one, but let's so let's put it underneath. Mm, mm. Well, that's not too bad, actually.
Good. Do you want to try your proof?
Sure. Save everything first.
Yes.
This is not going to work. So I just say find replace path of that comma path.
Right.
Come on, come on, come on, come on. Oh.
Okay.
Flap, 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 flap. Hold on, let me just.
I think I already tried that one. I'm not sure of it. I think it worked.
I need to go.
Yeah, hopeless.
If only we had a progress bar.
You can put progress bar on everything.
What?
So that you
Yeah.
can put progress bar on everything.
Sounds
No,
like,
that's okay.
sounds like a high school counselor.
Well, no, it's a. I mean, you can put a barber pole progress bar, but you can't put much else on everything.
What else remains to be done?
In what?
Well, for this, no, not for the whole piece, just for this section.
Well, I think that last one, I'm a little less tired. That last paragraph needs to be done.
Yes. Okay. That's okay. It's not too bad. We almost finished this section. Wow. We spent like 6 hours on just a small corner of that section. That was hard.
Yeah. Well, we got some nice pictures, though. I mean, these are,
Yes, we did. Yes, we
you
did.
know, look, realistically, some of these pictures like that guy is sort of a classic.
It looks nice. Yeah.
It does.
Yeah. Yeah.
I mean, these things will become, you know, if you, in case you haven't noticed, a lot of the pictures that were in like my early versions of stuff about the physics project have been like reprocessed over and over again.
You mean like beyond the summer and winter school?
Well, I mean, people have been, I don't know, you know, people like Jonathan certainly use them plenty of times in their papers.
Sure. Yeah. Yeah. Yeah.
I'm going to leave this running. What the hell? And I'm going to go to sleep.
I would kill it in case. I think I already managed to prove double negation from the Wolfram axiom.
You proved it? What?
You mean, yeah, cut eliminated.
Well, I mean, look, worst case is it crashes my computer. It's okay.
Okay.
I mean, it's not like this computer is, I mean, there's something probably to be said about the structure of all these things, but anyway, it's for another day. All right, good work. Yeah, I mean, it looks almost trivial, doesn't it, at the end? You have to realize it's like these examples in NKS that were like, oh yeah, there's just this random multi-way system that does this thing, you know,
months of
months
work.
of CPU time and
yes, many mouse miles.
Yeah, right. And the trouble is that yeah, I think some of these things people notice in the end because they try and reproduce them.
Yeah, but what's funny is sometimes
it is interesting.
Like
20 years,
take the shield for the Radiological Society, for instance. Sometimes you can quickly generate something that looks very complicated. You know.
Sure.
Sometimes it comes easy.
To that.
Yeah, right. And sometimes it's quite difficult. I think reading the text and looking at the pictures, I think I would imagine that these are difficult to generate because the ideas are complicated. The fact that you have both complicated pictures and complicated ideas that they represent,
yeah, right.
That makes for a work intensive combination, as we know.
Well, and the thing that we're not doing now that NKS did is these self-explaining pictures with all of this meta diagramology.
Right.
I mean, like were we doing that now, we would have in each of these things, like even for the multi-way systems that we have, you know, here we're just explaining in text, it's this rule and here's the multi-way system. Whereas in NKS, it had a diagram that allowed you to read the multi-way system without reading the text.
Yeah.
I forgot all of that stuff. I have to try to remember all that stuff because I'm going to write about it in the 20-year.
Why did you discontinue that approach?
Because it's really hard.
Fair enough.
I mean, it takes a lot of time, and it's one of these things that if you're making, here's the thing, if you're making something of minimal length that you want to be able to be read sort of sort of in a disembodied way, then you need that. But if you're prepared to have something where you expect people will read it, you know, in that case, one of the requirements was, well, I suppose part of the point of self-explaining diagrams, which actually worked pretty well for people like architects and so on, who are used to seeing diagrams.
Yeah.
And are not so used to seeing. I mean, it was kind of, you know, it was the avoidance of it because one of the things in these blogs is there's not any particular avoidance of code and formula like stuff. Whereas in NKS, it's just words and pictures. Right. So even these, yeah, anyway, and when they're formulas, they're just used as picture elements. All right, let's just leave this running. I'm too tired to think anymore. To be continued.
Okay. To be continued.
Okay.
Thanks, Stephen. Thanks, Nick.
Thank you.
Getting
Thank
closer.
You. Okay.
All right.
See ya.
You. Bye.
Okay. Bye.